Okay, thank you, Saravanan, for the introduction. And it's my pleasure to give the presentation here. And yeah, as Saravanan mentioned, so I'm from the Texas A&M University. I'm going to talk about the aerosol representation in the GCM, and this is the global climate model. Firstly, I want to acknowledge the founding agencies, the DOE Energy Earth System Model Program, and also the DOE Atmospheric System Research Program. And before I'm going to talk about the aerosol representation, I'm going to post some questions. And the first question is how the aerosol property and the process represented in the current GCM, and how does the model compare each other? And the second question, what are the major assumptions and simplifications in the representations? What are the weaknesses in the current representations? And the third question is, where are the trouble spots? What type of aerosol, which regions in which aerosols are not represented well, or simulated aerosols do not agree with observation. Then follow the question 2 and 3, and how can the current representations in the GCMs be improved by the process studies, and what aerosol process and property and process need to be better understood and parameterized. Okay, so this is the outline of my talk, and the first part I'm going to talk about the aerosol representations in the GCM, and I'm going to talk about how we are going to represent the aerosols, the size and the process, include the source and the sinks, and the property and like the physical, chemical and optical properties. And then the second part, I'm going to talk about the uncertainties in the aerosol process and the property in the GCM. And so I'm going to highlight a few major uncertainties which I think important, include the primary emissions and secondary aerosol productions and formations, and then the removal process for the aerosol from atmosphere. And then the third part is how can aerosol representation in the GCM be improved. So this is the outline of my talk. And so when we talk about models, so I just quickly go through a few type of models, and you probably heard about the box model and the zero dimension and the parser model and the single column one dimensional, and then the chemical transport models called CTM. That is a 3-dimensional regional global. But for the chemical transport model, the metrology is prescribed from GCMs or from analysis data, and then the chemical transport model can simulate the aerosol and chemistry, but there's no feedback of this chemistry aerosol on the metrology field because the metrology field are prescribed. And then the regional circulation model, like you probably heard about the WRF model, the weather research forecast model, and these are 3-dimensional regional model, and the metrology field predict with the boundary condition from GCM or analysis data. And what I'm talking today is not the GCM and the global circulation model. It's a 3D and the global, and the metrology field are interactive predict the wind, the temperature, and the humidity or that meteorology field, and the aerosol and online or offline, and depend on purpose. But today I'm going to talk about the online aerosol. The aerosols are interactively predicted in the GCM. And this is showing the component of the climate system which are represented in the GCM and the Earth system or Earth system model. And so this is showing this is from IPCC, and you can see this different the component of the atmosphere, land, ocean, and the sea ice, and land ice, and biosphere, and they are complicated interaction between different components to include the air-sea interactions, and atmosphere ice interaction, and land atmosphere interactions, and atmosphere biosphere interactions. And they also, like here, you can see anthropogenic emissions, like from industrial, and also there are volcanic eruptions are emitted, and within the atmosphere they are radiations and the cloud and the precipitations. Okay, and then you can see here it is show the gas species like greenhouse gas, and this also the aerosols. Okay, and you can see the aerosol it is a small component in the climate system, but it can play a very important role and in the climate. Okay, so I'm going to start from the first part, and on the aerosol representation in the GCM, and so how the aerosol represent the size and the process and the property of the aerosol, and so firstly, what are aerosols? Probably people know that, and so aerosol particles are aerosol and are particulate matters, which is a suspension of the fine solid particle or liquid dropping in the air. And one complicated things for aerosol compared with the gas, and is the aerosol has this pretty wide spectrum of size distribution, and it came from 1 nanometer, and this is to 10 micrometer, and you can see it's in diameter, and you can see this is like 4 orders magnitude size, but it can be important for the radiation. Okay, so for the different size particles, they have very different optical property, and also important for cloud formation, like cloud condensation nuclear. Its size are important. Another complicated thing is for the aerosol, it's a multiple composition, a complicated composition. It can include like we know that this like sulfate, nitrate, and ammonia, organic carbon. This is organic carbon can include many different type of the chemical compounds, and black carbon, that is important for the radiation absorbing particle and dust and the sea salt. Yeah, so this is complicated, and so it's include size and different composition, and this is showing this is Los Angeles smoke, and this is the haze in Beijing. Okay, you can see the visibility is only a few hundred meters, and this is because of the aerosol effect on the radiation, and so aerosol can come from two different types, and the first is the primary. Okay, the primary aerosol is immediate. What it means primary immediate from directly from the either from the surface or from from like from the Earth's surface. And you can see this is the sea salt, and this is the smoke, the wildfires, and the immediate the smoke aerosol, and this is you can see the dust aerosols. And this is another type of aerosol from the is a secondary. Okay, secondary, it means it's formed in the atmosphere, so it's not directly emitted. And so this is and this is this is like we know the sulfate aerosol, like the major type of the inorganics that is formed from emitted sulfur dioxide from power plant. And this is like nitrate is also important. The air pollution particles. This is it's from the automobile, like the emitted nitrogen oxides. Okay, these are gas species, and they can oxide and form the nitrate. And this is another major type aerosol, the organics, like secondary organics. These are from from trees. You can see the tree emitted some volatile organic compounds like gas. These gas chemical species, this VOC can be oxidized in the atmosphere. They can form the organics aerosol. And so this is showing the aerosol size and the composition, and you can see here there's the aerosol size, and as I said that this aerosol size can span a few orders of magnitude from 0.001 micrometer to like up to a few tens micrometer, and in the atmosphere, the aerosol size distribution can follow these not like normal size distributions, and you can add the shape of the particle size distribution. And so you heard about the PM 2.5, right? So the PM 2.5 is the particle diameter less than 2.5 micrometer. So we call like fine particle. And then also above that is over that size is coarse particle. And for these different modes, like normal mode, we this here like a nuclear mode or echo mode, and this is the accumulation mode, like between 0.1 to 1 micrometer, and less than that is echo mode or nuclear mode. Or above that 1 micrometer is like coarse mode. And depend on size, and these like most the coarse mode particles most from the primary, like the wind blow dust or from sea salt, and these are by aerosols from the most in coarse mode. And in the fine mode, in the fine mode, these like the fine particles, the nuclear echo mode, accumulation mode, these aerosols are most from the secondary production, like the chemical reactions form the vapor. They can nuclear form the new particle. These new particles can grow and to form the big particles. So this is the chemically produced in the atmosphere. And so how we can represent these aerosol? And currently there are mostly three type of three approach to represent aerosol. As I said, we need to represent the aerosol size, aerosol size distribution, aerosol composition, and aerosol and you see the simplest treatment is we call the bulk approach. So basically, we only predict the mass and the mass concentration, like we predict different composition, the mass of the composition, because we only predict the mass, therefore the size is prescribed. We don't predict size. And then you can see for different composition, like sulfate, organic, black carbon, they are assumed the external mixed means they are not mixed together. And we know that is not correct, because in the atmosphere, these different compositions are internally mixed together. And this is the simplest approach. And this is another approach called a moment-based or modal approach. Modal approach assume the aerosol size, aerosol distribution follow the, here see the in the observed in the observation show this is the log normal distribution. Okay, so that it has followed that log normal size distribution, and then the model predict the mass and then the certain moment and the number concentration in each mode. So for that mode, we predict the mass and the number concentration of particles, and then we assume this that log normal distribution has another free parameter is standard deviation. We prescribe standard deviation, and to often assume the internal mixed within the mode aerosol internally mixed, while the aerosols are external mixed between the modes. So the internal mixing is very important for the radiative property. If the black carbon, if black carbon is coated by other non-absorbing particles, it can enhance the absorption of black carbon. So the mixing state can be important. And this is the modal approach. And the most comprehensive approach is called sectional. So basically, we cut the size distribution of aerosol into different beams, and then we can predict that within each beam the mass and the number concentration and of aerosol within each beams. But this is can often pretty expensive for the GCM, because the GCM we have to consider the computational cost, because the GCM has to be run for multi-central simulations. Therefore, the computing cost is a concern. Okay, so I'm going to highlight a few aerosol model currently used in the GCM, and so the first this is the CAM model. This CAM3. This is probably more than 10 years ago. This is in the ANCA model. This is the National Center for Atmospheric Research. They use this is the bulk aerosol model. So as I said, the bulk aerosol model, they only predict the mass of different composition, like sulfate, ammonia, different composition, and the model don't predict the size distribution, and they sort of hybrid. They have for sea salt and the dust. They cut it into four beams, and because the size the dust sea salt, they can have a large size range. So this is the bulk aerosol, but because these bulk aerosols cannot predict size distribution, we know if we know the aerosol indirect effect on climate, and it's critically dependent on the size. Therefore, I have been leading the development while I was at the PNL, Pacific Northwest National Lab. We have developed they call the modal approach, the second approach. They call the modal aerosol module for the MAM, and this is for the ANCA CESM Community Earth System Model version 1. And when we first developed that, we developed the 7 mode. So basically, that is depend on size, range, active mode, accumulation mode, and so we represent by a log normal distribution. And within each mode, accumulation mode, we predict the mass mixing ratio for different composition, like sulfate, ammonia, and the sea salt. And so we have accumulation mode primary carbon mode. Primary carbon mode is particularly important for black carbon and organic matter. And this primary carbon mode, once it's emitted, so we consider the aging process called condensation, coagulation, and this aerosol microfluidics process, they can age into the accumulation mode. So they are basically mixed with other chemical species. They age, become into the accumulation mode. Then we also consider the dust and the sea salt. And they are like the 31 chemicals, aerosol tracers added. And of course, that's adding computational cost because we adding more tracers, and we also predict the number, and therefore the computer time is almost doubled compared with the bulk aerosol model. And then later we'll find out this increased computing time is quite significantly. Then we make some assumptions because we want to develop to simplify the version, and then we merge. Basically this is like the primary carbon mode include the organic matter black carbon. So we merge that into the accumulation mode. We assume it's an instantaneous aging process. Now we merge the dust sea salt with the accumulation mode, and the cost mode dust cost sea salt merge in a single dust mode. So at the end we only have 3 modes, and the echo mode, accumulation mode, and cost mode. So this is the we have 15 aerosol tracer, and the computation cost is increased by 30% compared with the bulk aerosol. And this is called 3 mode. So we have 3 mode with MEM3, and then later we find out that this is used in the CSM1. If people use the CSM1, this is the default model is MEM3, and later on we find out that maybe this is the simplified version is too simple and too simplified to make, and then we find out this have a big issue for black carbon because we assume the black carbon instantaneous aging, and then it's because it's aged. If it's aged into the accumulation mode, it mixed with other soluble species, it's getting removed very quickly. And so we find out, see here, this is the comparison with the polar region at the few sites, and Barrow, this is in Alaska, and this is in the Antarctic Haley site, and then you can see this is the observation. This is the seasonal cycle, okay, from different months, and the black carbon. You find this is from the MEM3, and this is the black curve. The black curve is from MEM7, and so when we make, you can see the MEM3, just the black carbon simulated from MEM3 is a significantly smaller than observation. The seasonal change is not correct, and then we found that because the black carbon can effect on the radiation effect on if it's black carbon deposit on snow and ice, it can melt snow and ice. It could affect our Arctic climate. Therefore, we adding additional mode based on the MEM3, and we just reinsert the primary carbon mode into the aerosol mode, into the MEM, and we explicitly treated the aging process of the organic carbon, black carbon. Yeah, so you can see the MEM4. This is reproduced the MEM7, and agree observation better than the MEM3, but you can still there's a large bias, and this likely due to the wet scavenging, removal by precipitation, and also emissions. Yeah, so this is from the ANCA CSM model. So if people using the CSM2 model ANCA, this is the default model is MEM4. Okay, And it also used in the DOE Earth system model called energy X-scale Earth system model, DOE model. It's used in the MEM4. And I'm going to highlight a few.
Xiaohong, if you don't mind, I have a quick question for you. I just want to
go ahead.
Your previous graphs. So if I understand, you this various modes means that you have a mixture of log normal distributions representing these particles, and you're talking about mixture of 4. Can you just give us a big picture of, we have this Earth system model with this grid. I guess some of these being are forced into the system aerosols, and maybe some of these are just result of kind of calculations. So exactly in the big picture, how are aerosols kind of fitting into the overall model? Can you briefly tell us?
Sorry, can you repeat again? I couldn't hear you very clearly.
Because I guess it's very new to all of this. So you have this Earth system model which is moving, incrementally over time, and you have these grids. And maybe some of these aerosols, which you're probably modeling as mixture of log normal distributions, they are being introduced to the system. So you can correct me, And then being generated, how they're evolving,
The aerosol, we represent the aerosol by these log normal distributions, like say in the accumulation mode. So accumulation mode is follow the log normal distribution, and but this is the shape of the side distribution is follow log normal. This for log normal distribution, there are three parameters. So it's the mass, number, and also standard deviation, like the width of the log normal distribution. This if we predict the mass and the number, we basically the log normal distribution has three parameters. Now we assume the width of log normal. So basically, if we have three parameters, then we fix the side distribution. So we can predict the side distribution. All these side distribution are freely evolving in the atmosphere because we depend on the number and the mass. So basically, these side distribution are evolving in the atmosphere, depending on the location, depending on the So, but this echo mode, accumulation mode, they have different size range. Right. Does that answer your question?
So that, I guess what you're saying is that the number and the size are being modeled by log normal distribution, and you're fitting parameters to those distributions.
The shape. Let me see. Go back. Okay. So this log normal distribution. It's the aerosol side distribution follow that shape, and then for this side distribution, these are three parameters. One is so if you know the three parameters of the log normal distribution, like this is the size, and also the height or the magnitude of the log normal, and also the width. So basically, there are three parameters. If you fix that, you can. If you calculate, the three parameters, you can just fix the distribution. So in the model, we predict the mass concentration of each for that mode, the mass concentration and also the number concentration, and then we assume the standard deviation of that mode. Then we can know the side distribution of that mode. But that mode is changing in the atmosphere because the size and the mass and the number are evolving. So mass and number are free parameter, are predictive parameter in the model.
And then
only the shape is prescribed.
And how does the dynamics of the system affect aerosols?
Dynamics. That if you have wind and so it's changed the aerosol is transport, and also if you have the cloud and precipitation that can remove this aerosol. The dynamic system, So in aerosol, like in animals, you have advection, and you have the turbulence transport, and this convection. This these are transport. These are tracers. So the mass and number are tracers. Therefore, they are transported by the circulation.
Thank you.
You're welcome. And yeah, so they are free parameters. So they are, yeah, so they are tracers. So basically these are individual tracers, like the number mass. So for the number and these aerosol, this sulfate mass mixing ratio is one of the tracers. So basically we were predicting these tracers, then we can know the size. Okay, there is another. I'm highlighted another model. This is it's ACM. So this is the ECM model, ACM model. They also have an aerosol model. The similar approach they used they have also seven they call it M7. Okay, they have nucleation ACM accumulation cosmos. So you can see the aerosol. This is the soluble mode and the insoluble mode. So this is different colors, different chemical species like sulfate within this mode, and this also black carbon, and this particularly organic matters. Yeah, so this is like in the insoluble mode. They have POM, primary, particularly organic matter, and also and black carbon. Okay, so yeah, so this is a similarly approach used, and this more complicated approach is the sectional approach, and this I'm going to highlight that also including the ANCA CSM model is one configuration. So you can see here this is called the Karma aerosol model. This as I said, for the sectional model, you divide the size distribution into different beams, different sections. Yes, you can see here they have sulfate. They have like they have a variety of the sections for the sulfate, and then for they have another group of the sections to represent a mixed particle like sulfate mixed with other chemical species. So you can see they have a different beams too. So therefore, you're adding more tracers. Basically, which each beam they predict the mass and number. So you have two, and mass is for sulfate, and so like you basically in this case you have two tracers, and this is for CAM for the MEM aerosol. So you can see we have MEM3. As I said, we have this is log number, these modes, and this is the range of the modes, and this is the size. And so you can see for within each mode, these are different different species. Okay, this is the MEM7. Okay, 7 mode, and so. I'm good. Yeah. So this is for this representing, we need to also consider that this is like for different approach. I mentioned 3 approaches. That for the aerosol module, we need to add in. We need to implement different aerosol process. This is a diagram showing the aerosol life cycles, and you can see the aerosol, this is primary emission. I mentioned the emissions, and so this the different aerosol tracers, they are transported in the atmosphere, and if the aerosol lifted by the parcel, if the parcel reach the super saturation, like this aerosol can be activated, and they can activate the aerosol, become the cloud droplet, and then if the cloud droplet form the rain, okay, and if the rain precipitating out the cloud, then this aerosol within the droplet, okay, this removed by the precipitation process, and then also below cloud scavenging, and if there's aerosol below the cloud, and these aerosols get removed by the precipitation. And so this is called the nucleation scavenger. So aerosol activate become droplet, and then droplet form the rain. So aerosol in the cloud droplet get removed, and this the cloud is not just the removed aerosol; it can produce the aerosol. You see that, and this is the nice sulfur dioxide, and they can they can oxidize by this hydrogen peroxide from the sulfate, and if the cloud evaporate, this aerosol from the cloud droplet can just expand into the atmosphere. In fact, the majority of the sulfate aerosol is formed in the cloud, and so now 70% of sulfate aerosol is formed in the cloud, evaporate, and so this cloud process, and then there's other clear sky process like the SO2 oxide, a lot of chemical reaction involved, and so like sulfur dioxide is from the sulfur acid gas, and these aerosol sulfur acid gas can have to form the new particle called the nucleation process, and as new particles can grow, and by condensation coagulation, they become larger particles, and then the aerosol can have called the sedimentation dry deposition, and this is the aerosol life cycle, and so I'm going to quickly go through some process, and one is the emission, like the primary emission. So in the model, usually this for this the emission is online. So like this basically from the emission inventory, like the people, the model participate in the IPCC assessment. The IPCC usually provide these emission inventories. They can for different this is for different species, and then in the model there's like sea salt dust. They usually online calculate depending on wind and the conditions, and this also importance is the wildfires. By mass burning areas can be the injection height is also like so where you put this emission like at the different vertical levels, it can be important. So for the transport, if you aerosol put that above the boundary layer, these aerosols can transport and long distance. Or if you put that near the surface, these aerosols can be removed quickly, and the injection height can be important. And this is so as I said, a lot of aerosols formed in the atmosphere. So one process like this is the aqueous chemistry that I already mentioned. That in a chemical reaction produce taking place take place in the cloud droplet. They can form the sulfate aerosol. Then if the cloud evaporate, they can the aerosol can just expand into the atmosphere. And so this is the model. How they treat the bulk model. It's another model treated this process, secondary sulfate production. Depend on the complexity, like the bulk model, and about model model, B model, they can also treat this microphysical process, like the nucleation condensation coagulation. This is important for the size distribution, and this is why the model and the beam model they predict the size. While the bulk model they just neglect this microphysical process because they don't bulk models do not treat the size. And so let's see the SOA is the secondary organic aerosol is a major type of aerosol. This is a lot of studies looking at SOA, the secondary organic aerosol. This also depend on the different complexity. Okay, the early model is very simple, like they apply some yield to from the isometropy emission, like from the forest, from trees. And then now the more complicated SOA, like using the VBS, volatility-based set, it predict the volatility of the organics. Depending on organic, the volatility these organics can condense on the aerospace, and so to form the SOA. This is showing the one of the treatment in the ACM model, in the ECHAB model, and like treated the VOC, volatile organic compounds from the forest. They can taking place in the chemical reaction. They form the different volatilities. They can condense on the aerosol to form the SOA. Another major process is the microphysics process. Is the new particle formation, or called nucleation. Nucleation is the major mechanism for form the new particles. This is showing that firstly there's small clusters or molecule formed by the like sulfuric acid gas, and combined with water vapor molecules become. And if it is enough sulfuric acid and all organics, this cluster can be stabilized, and then they can grow to form the large particles. And this you can see, this is mostly in the one or few nanometer size range. This is new particle formation, and so you can see this is I'm showing this is from one measurement. You see this is the different days, and this is the size. And the size, you can see this is the size, this is the 1 nanometer, 10 to minus 9 meter, okay. And you can see this is new particle formation, very small, only 1 nanometer. These particle form, then they grow to the big particle. This is size increase. So this is this is the one event, new particle formation. This is another event. So you can see how these new particle form at the small size, they grow to the big particle. Into this size range, they can serve as a cloud condensation nuclei, can influence cloud. So within this size range, so they grow particle, they form and grow. And so the aging process, I already mentioned for the aging, like for this aerosol, like the black carbon, organic carbon, they can age if they are insoluble. Then, but in the atmosphere, this particle can age by mixing with other soluble species. They can age, and they can coat it by soluble species. Then they can remove it by the cloud, because if they are soluble.
Question.
And, so it's okay.
Could you go back to the slide where you showed aerosol particles as a function of time? Yeah.
This one?
There seems to be some periodicity in this growth. Is that coming from some daily cycle or something?
Yeah, usually the formation is early morning, because new particle formation depends on the temperature, depend on the humidity, as I said. Temperature, if the temperature is cold, this particle can be easily become more stabilized, and also depend on water vapor. If you have more water vapor, it can also more easily stabilize. This is showing this diagram. So basically, if the temperature is colder and if there is more water molecule, it can more easily condense, stabilize. This is why the nucleation event is depend on meteorology. It's happen in the early morning usually, but it depends on also on the concentration of the precursor gas.
Thank you.
Welcome. And so this is okay. So this is the aging process, and for aerosol process, also the water uptake. The water uptake is important. If you look at the aerosol, like this aerosol particle, not just dry. This aerosol absorb the water. So this is most of the mass can be water on the aerosol. So if the aerosol is soluble, they can uptake the water. And so this is the model generally using the color theory or kappa color theory. Kappa is kind of high opacity, depending on like the solubility of the particle. They can absorb the water and then can increase the size. This is showing another process, the uptake. And the aerosol usually stay in the atmosphere a few days. Okay, this is because of the removal process, and this is showing the dry deposition and the wet removal, and so this is the dry deposition. Of course, depend on the. So these are representing like based on the serial resistance approach, and we can these aerosols can remove from the atmosphere. And another wet removal is a major process for the fine particles. As I say, these aerosols activate from droplet, they can remove if the cloud from the precipitation. So this is the process, the removal process. So this is critically depend on the cloud microphysics. Like if you form how much rain you form, precipitation you form. If the cloud is not precipitating, that means that aerosol will just suspend. Okay, and so this is the aerosols are not removed. Okay, this this is process. Highlight this is property. Also complicated. The aerosol property is you have to consider mass, compositions, the composition like different type aerosols, different composition, and the size and the mixing state, how these aerosols mix together, and that could affect on the radiative property of the aerosol and the hygroscopicity, like that. If the water, how the aerosol absorb the water. Okay, this I'm quickly go through the uncertainty. So uncertainty, it is the aerosol process in the GCM. So I'm going to highlight the primary emission and the secondary aerosol formation, then the removal process, the aerosol removal, particularly the wet removal, and the uncertainty in the aerosol process. One is the emission. Okay, one is the anthropogenic emission, in the developing countries, I'm going to highlight emission in China. Actually, this is a large uncertainty, even like for how much emitted black carbon, the primary organic matter, and still this large uncertainty is for the emission, and another emission is for the primary emission, like the biomass burning. Like the smoke, like the agriculture burning, these are large uncertain, and even for dust sea salt, these are differ quite large. Like between the models, you can see it's sea salt dust, and the emissions are large uncertain. And I'm going to go through a few slides showing the emission. And when we develop our aerosol model, we compare the aerosol object depth. So this is the aerosol object depth, and this is, you can see a seasonal change and at different site. This is in the North America, and you can see the model is the different two lines. Okay, MEM3, MEM7, and this star is from the observation. You can see the model agree with the observation surprisingly well. Okay, that is for the North American side, and these are different stations. And however, if you look at the comparison in the East Asia, and the model is doing very poorly. And this is the side in Mongolia, and in this is the desert side over desert, in the desert. So you can see this is highlight the dust emission. And if you look at the cities, okay, this is like Osaka, Seoul. This is the Eastern China and the Taipei. So the star is from observation, and the model is just so that you can see the different two lines. The model significantly underestimates the observation. And so we are wondering why the model is doing so poorly in the East Asia. And it's not just our model. This is the CAM, the ANCA CSM model. And you can see this is from the IPCC AR5. Okay, this is the ArcMap, ACC map. This is in the comparison, chemistry in the comparison. And they also find out this is different regions like North America and Europe and North. this is North East Asia, and you see different models, and you can see the model all significantly underestimated has a negative bias over East Asia, and for all these models, and then we try to figure out why, because this is the comparison AOD doesn't give us a lot of clue about which chemical species are responsible for the negative bias, and so we just compare with the observation data from China, and there are 14 sites in the China. They measure the chemical compositions, and also there are some sites and measure the AOD. This is aerosol oblique depth, and also some aeronet satellite. I'm going to highlight that. Then we compare with this ACMID, so the chemistry model comparison project from IPCC-L5. This is from observation. We add sulfate and nitrate ammonia different. This is from the observation. The blue from observation, and this is from the model. This model from, and you can see the model doing very poorly. Okay, underestimated, and even the seasonal change are not correct. And so we find we trying to look at why. So we want to look at the emissions. We look at and also another chemical species, nitrate, and usually nitrate is not represented in the model, but it can be important in the polluted like industrial region. And so we look at so first we look at the aerosol emission in East Asia. That we, instead of the IPCC-L5 emission, this is used in the IPCC-L5, and we also implement another emission called MAKE. This is developed in the Tsinghua University, and this is basically they are developed by Chinese scientists. They call it MAKE emission, and we implement that in MAKE emission. This is showing the comparison of the MAKE, and this is the solid line like SO2 from MAKE, and the dashed line from the IPCC-L5. Okay, it's for different composition, and another thing is we just treated the nitrate, and nitrate is it is pretty hard to treat, and we are using a module called a Mosaic. Okay, I treated the nitrate, and for the nitrate partition between the gas and the aerosol phase. And this is you can see after we implement the emission, I implement the Mosaic for nitrate. You can see this is the original model. This is the ANCA model using AR5 emission, and this is from the MAKE using the MAKE emission. This is using both MAKE and also treating nitrate, and this is the aerosol oblique depth, and this is comparison with the MODIS and MISA. This is satellite. You can see after we considering the emission and consider nitrate, and the model agree with the observation reasonable well. So we find out that emission account for like 20% of a bias, and the emission nitrate account for like 60 to almost 90 of emission bias, AOD bias in Eastern China. And also if we compare with this site, this candidate site, so you can see this blue is from the observation, the red is from model when we consider both the new emission and also nitrate and ammonia. So the model doing well. And see, this is when we consider new emission, this is the old AR5 emission, IPCC-L5 emission. This is the observation for organic carbon, black carbon. It's still underestimating, means the MAKE emission may be still underestimated the emission compared with, yeah. And this is, but you can see sulfate is still a big issue. Yeah, I'm not going to touch about that for sulfate. Yeah, so this is so I'm talking about the emission uncertainty and also the nitrate. Nitrate is the secondary aerosol. Okay, and this weather removal is I'm going to highlight the weather removal. Another uncertain process is the treatment in the GCM is the weather removal. And of course, weather removal depends on the cloud and depends on precipitation. And so this is I'm going to highlight two slides. This is showing the this is the 16 models, okay, and the 2/3 of the 16 models, the maximum divided by minimum, and this is aerosol object depth. This is the aerosol mass, column mass, and you can see in the middle latitude and in the equator tropics, okay, in the lower latitude and middle latitude, the agreement between the model are reasonable well. If you look at this, these are blue. This is about 1. Okay, this means the maximum and the minimum is agree with each other. And if you look at the high latitude and Arctic and Antarctic, the difference are like up to 10. Okay, if you look at maybe even higher for the in the Antarctic. So the transport cannot explain the large uncertainty between these models. Okay, and more than 10 times uncertainty. This means large uncertainty could come from the weather scavenging, and so because the aerosols are mostly emitted or produced in the middle latitude, and then once they transport into the remote region, they are getting removed. As the weather removal is the large uncertainty. I'm also going to show you the vertical profile, and this is the vertical profile of the aerosol black carbon. And compared in the tropics and the middle latitude, this is the pressure, and this is black carbon at a different field campaign and by NASA, and you can see this is black curve is from observation. In different lines, like the spaghetti lines, are from different models. They differ by maybe 10 times, 100 times between the model, and so particularly in the free troposphere, and so this is they relate the scavenging, and this is from BC. And if you look at in the high latitude in the Arctic, you can see the field campaign, and this black curve is from observation. There's different lines from different models. You can see that differ quite substantially. And okay, this is I want to highlight the last is our. You can see this is a more recent field campaign. This is NASA ATOM campaign, as from pole to pole, and this is the NSF HIPPO from pole to pole, and this is based on for the CSM2 model, and you can see default model is also have high bias compared with observation. Is dots and square, and once we improve the aerosol the convective scavenging convective process, because these up troposphere mostly by convective transport, then we found this is the blue lines. Well, we can see that the model agree with observation reasonably well once we improve the convective process. Okay, so I'm going to the last one, the aerosol representing improvement, and the process, and we need to improve the emission, and the aerosol nucleation growth, and showing the production, and the weather scavenging, the property, the hydropacity and mixing state, and the brown carbon, the refractive index for brown carbon. Yeah, so this is the aerosol representing can be proved, and let's see. Yeah, so I highlight that we need to start from we need a field campaign and the laboratory and the field measurement, and then to improve the aerosol, to improve understanding of cloud and aerosol process and the property, and eventually improve the aerosol representation in the global model. And yeah, so this is the last one. Thank you very much. And this is the material in my slides is this is the book in one of the book chapter. Okay, that is in press. The book is a fast process in large scale atmosphere model, permeabilization, evaluation, and observation. So this is I have a chapter talk about aerosol and climate impact. So if you are interested, that book should be published very soon, and this is in that chapter. Okay, thank you very much.
Questions from the audience? Any questions from the, no, let's, audience, any questions for Dr. Liu? Oh.
So Dr. Liu, so, I guess often we are interested in the climate model to get a sense of how much the carbon dioxide will be many, many years later, how much the temperature change will be across regions. So what kind of aerosols are these things more sensitive to? Which aerosols are more important to model correctly? I mean in terms of size and number.
Yeah, so so this is actually you have to represent all type of aerosol well, actually. So this is why it's hard. So the aerosol, you cannot neglect of course the aerosol depend on regions and let's see we have to represent the black carbon, like if for the absorbing, so we have to represent black carbon, and in the industrial region, and we have to represent like this for these organics, and also the sulfate and this nitrate, and in this in the Wi-Fi in the South Africa and South America, these are Wi-Fi's. We have to also represent this and this smoke aerosol. This is why these are challenging. We have to represent all these type of aerosol, all these species, and so we have to represent all these type of aerosol, and because the dust, they can have different effect on like dust. This can influence the biogeochemistry cycle. They can this is we have to represent, but depend on the regions. Like some aerosol is dominating over regions like this. This over industrial regions, sulfate and nitrate important, but over other regions like the smoke can be important, but over the ocean, the sea salt important.
I see. And also, very quick question now. So from parameterization, I understand you mean that you have a probability distribution of, again, numbers and size of different aerosols, and you change their parameters as you go along. So everything is deterministic in your model. There's no randomness per se. You don't, you just assume that the probability distributions change from time to time. There's no kind of randomness in the amount that's being changed. Is that fair to say? Your model is deterministic in this sense?
Yeah, let's see. So this is the aerosol tracer. This is like tracer in the atmosphere. So basically, it's effect on by the meteorology. So if you have randomness of the meteorology, like that could affect also aerosol process.
I noticed that these aerosols are typically treated as tracers, right? Like, does turbulence enter the picture somewhere? Like, for the bigger particles, at least there should be preferential concentration.
Yeah, so this is a tracer. So they influenced by the turbulence also, right? So if you turbulence motion, they can at the surface, if the near surface, if the ADs, they can mix the aerosol with the surface. They can remove. The aerosol can remove they can stick to the surface that can be removed by the dry deposition.
So, but if the particles, like, they can move differently, like not behave as tracers, right? That's what I was asking. Like, the bigger particles can preferentially concentrate and coagulate more than otherwise accounted for.
Yeah, some big particles, they are like coagulate with each other. Yeah, in the atmosphere. And right, is that
Actually, maybe, hi, Xiaohong, can you hear me?
Yes.
Okay. So first of all, thank you very much for staying up late and for your talk. I've got a very naive question, so please forgive me. One of your last slides emphasized again the importance of field work, I think. And I assume there's a regional aspect to the concentration of aerosols and so on. Now I'm wondering whether there is a case for gathering data better, say, which is specific to India or South Asia and so on. And in particular, and I'm asking you, but also the audience for subsequent discussion. For example, TIFR has a wonderful balloon facility. India has a wonderful balloon facility where we can easily go up all the way up to the mesosphere, actually. And the question is, would there be a case for, therefore, using such facilities to gather data about aerosols? Okay, thank you.
Yeah, yes, thank you. And for this, if the balloon can, so this, if you can put the aerosol instrument on the balloon, that it can like aerosol size and aerosol number concentration. You can measure the vertical profile of the aerosol, and as they showed here, these are mostly by aircraft. This the observation from aircraft, and but if you have a balloon, you can also measure the vertical distribution of the aerosol, or even the mass or number of. So you can the vertical profile can be important, and like the volcanic eruptions, they can inject the aerosol into the high up, right? So we need some like into the stratosphere. So we need a balloon. If the balloon can measure the aerosol, we can look at the aerosol in the stratosphere. The vertical distribution here, currently the model has a large bias, and therefore we need a vertical distribution.
Thank you.
The data to help us.
So Xiaohong, I think I have one final question. One thing that's of concern in India is the pollution in Delhi. You might have heard about that. It's pretty bad in the winter. So do you have any advice or information on model studies of that, and what we can learn from model studies of that, or it's still too new for model studies, the pollution over Delhi?
Yeah, we need firstly we need observation data, and so we need a chemical composition. I measured what type of aerosol, and with that we can do some modeling studies to see if we understand the formation mechanism, like a lot of aerosol is formed in the atmosphere, and we can see if the model is doing well now. But we need to firstly have some data to validate the model. That's what I said, that we need some data, and then then we can use the model to help us understand some physical chemical process. The model may be not doing well. I think maybe in India, the same case. I show in the case that the model not doing well in China, East Asia, and that could be also they have bias in maybe India. The model in India have some similar issue, that emission maybe not represent way like India have like the anthropogenic emissions. Also India have the biomass burning, agriculture burning. It can be important in the springtime. It could also, if this emission has an issue, but the chemical formation could be also. We need to understand that if the process help use the model. But first we need the data. Maybe at the better long-term data for model, for global model. If you have multi-year data, that is better.
Thank you, Xiaohong. Thank you for staying up again. Keep the talk.
Okay. Thank you.